Okay, so shall we resume? Okay, so similar to like how we approached the dynamic programming solution, like we're going to start with the prediction problem, which is basically given a policy, I want to compute the value function. So then we will talk about given the value function, how to compute the policy, and then we will combine these two in the framework of GPA so that we get, eventually we get the Monte Carlo control algorithm, like which will interact and learn the policy. Okay. Okay, so first we will start with Monte Carlo prediction. Okay, so as I mentioned before, like in the case of prediction, it's an evaluation problem. So given a policy pi, okay, we want to estimate. First, let's talk about estimating state value functions. Then we will talk about how to estimate action value function. Okay, so we want to estimate V pi of S. Okay, so what is V pi of S? V pi of S is basically the value of a state S, okay, under policy pi. Okay, now in this case we are doing sample averaging. So basically, given a set of episodes obtained by following pi and passing through S. Yeah.
Can the value of a state change depending on where in the episode it's encountered?
Okay, so that's a good question. So like what happens is if you see the value, like if you see the state in many parts of the episode, right? So we are going to talk about that now. But can the value change? If you think about it, it should not change. But maybe when you're practically estimating, it's going to change, obviously, right? So theoretically, a value of the state tells you what is the possible return from that state.
Yeah, but if you encounter the state,
when you have loops, so when you have loops, I think it's a bit complicated. Like I need to think about sample averages would of course change, but I need to think a bit more about the actual value. So it doesn't make sense for the actual value to change depending on when you're visiting, right? So it's a bit tricky situation. So that's exactly what I'm going to talk about right now. Okay, so each time you visit a state, okay, so we're going to call like each occurrence of a state, yes, in an episode, okay, so we're going to call that as visit to the state. Okay, now as he rightly pointed out, you can visit a state more than once in an episode, right? Then how would you estimate the value of the state? Because the sample average from the first visit is going to give you a different value. The second visit is going to give you different value, and so on, right? So now there are two ways in which you can approach this problem. Okay, so depending on which you're going to call your Monte Carlo method as first visit Monte Carlo or every visit Monte Carlo. Okay, so the first visit Monte Carlo, okay, it actually estimates V pi of S as the average of returns following first visit to S. So this is simple, consistent with our definition, right? Like, so our definition is every state should have one value which tells what is the return from the state, right? So it's kind of confusing when there is a loop. The first visit Monte Carlo just makes it simple and says that you consider only returns from the first time you are visiting the state. So that is the value estimate of the state. Okay, yeah.
just to be clear, by first visit, you mean first visit in the trajectory, right?
First visit in the episode.
Okay.
So let's say I have an episode which looks something like this. I start from state 1, okay, and then I move. I'm just going to talk about states here, not actions and rewards. Okay, so I start from state 1, and then I move to state 2, state 3. Let's say then I go back to state 1, and then I go to state 4, and the episode ends. Okay. Now the first visit MC will only consider the return for this particular visit. That is the true value function, or at least that's the true value function that first visit MC believes. Okay. Now, one can also think about every visit MC. Okay, which basically averages returns following all visits to S. Okay. Now, in this case, I will consider the return. So let's use red for every visit. Every visit would consider return for this, and it will take an average of these two. Okay. Now, theoretically, it's kind of easy to analyze the first visit approach because the first visit MC is very similar to our like action value estimate in really in bandits, right? So, like if you think about it, you have, let's say you visit the state infinite number of times, then this sample average of first visit MC will converge to the actual value function of the state, right? Now, every visit also converges to the actual value function of the state, but it is kind of less clear how it is doing, but we are not going to talk about it now. But I just want to make a point that every visit is not a crazy algorithm, like it also converges to the actual value function. It is just not very intuitive, like why that should be the case. Okay, so now we have a very simple algorithm to do prediction or policy evaluation, right? Like you give me a policy, I'm going to use the policy to act on the world, collect episodes after episodes. I will consider the first time I'm visiting every state and use that to update the value function. I will repeat this forever, like whenever I want to stop, but like forever, yeah?
Are we still in following that Markov property?
Yes, so
in that case, like I think every visit it makes more sense, right? Because otherwise I'm just simply ignoring the data from the second visit of S1.
true. So
Not completely ignoring because it's kind of
oh yeah, that is true. But I'm not saying one is better than the other. Like in fact, every visit is going to converge probably slightly faster than first visit because you have more samples, right? Like so your observation is valid. But I was just mentioning the first visit is easy to analyze. Like, but every visit should be better than first visit. But one reason why we will study first visit is because when we move to function approximations and when we move to like when we build more on top of these algorithms, it is just very intuitive and easy to extend first visit than every visit. So that's one of the reasons why like I want to discuss about both. But your observation is valid. Okay, so now here is the algorithm. Okay, so this is basically first visit Monte Carlo prediction. Okay, where you have a policy that you want to be evaluated. So as usual, we are going to arbitrarily initialize V of S. Okay, and for every state, we are going to have an empty list for returns. Okay, as you can see, this algorithm is not optimized for the incremental update that we had in bandits. You can change this to incremental updates if you want. So this is going to be a memory intensive algorithm in the sense for every state, I'm going to just put all the returns in one list. And whenever I want the estimate, I'm going to average it. Okay, so that's what is happening here. So you generate an episode following the policy. Okay, so once you have an episode, you want to compute return with respect to each state, right? So if you remember the recurrent equation for return, right? So GT is basically the reward at the t time step plus gamma times GT plus 1, right? So my return from my current state is the current immediate reward plus gamma times the return from the next state, right? Now I can actually write this recurrence backwards. Okay, I can start with the final. Okay, maybe I'll give you an example for this. So let's say I get a reward of 1, 2, 3, 4, 5. Okay, let's say we are in an undiscounted setting, gamma is equal to 1. Now what is the return for this state? 5. What is the return for this state? What? 9. Somebody said 4. It's 9, right? So we're talking about returns. So what about return for the state? 12. Return for the state is 14, and return for the state is 15. Right? Yeah.
For gamma equal to 1.
Gamma is equal to 1. Yeah. So we are in undiscounted setting. Okay. Now you can see that I can actually start from the back and compute the return for all the states by just adding the rewards, right? So that is exactly what is implemented in this algorithm. So you start with the return of 0. For the starting from the last state, you're going backwards. Now, unless the state t appears already in the trajectory, if this is the only visit or if this is the first visit, okay, then you append that to the list and you take an average. So whatever I explained for the last 5 to 10 minutes, that is summarized in this algorithm. So any questions about first visit Monte Carlo?
Like when you generate an episode, do you like need to know the whole episode before, or you just interact?
Yes, you need for this algorithm. Okay,
We need because
you need the entire episode because you want to compute return. But in next week, we are going to see algorithms where you don't need to wait for the episode to end. Okay, so but for this week, like we will assume that we have an episode and the episode ends. Now, as you can imagine, this algorithm will not work for continuing tasks, right? So this works for episodic tasks, but the thing ends at some point. When you have a continuing task, when there is no ending, it's not very clear how to use first visit MC. Any other questions? Okay, so now let's talk about the backup diagram for the first visit MC. So if you remember dynamic programming, like the backup diagrams for dynamic programming look like you start from a state, you look one step ahead, and you sum over all the value functions like or estimates, and basically you back up that to the current state, right? So now in the case of Monte Carlo methods, you start from a state, okay? Now you consider the entire episode starting from that state. So from this state, you take an action, and that takes you to the next state, and then you take an action, okay? And this continues until the episode ends. Okay, so you go all the way to the end of the episode, and then you compute your return. So you're backing up from the end of the episode to this current state. On the other hand, if you remember about DP, it's kind of bootstrapping approach, like where you have current state. If you're doing state value function estimation, then you have multiple possible actions. Then for each possible action, you had multiple possible next states, right? Now you know the value function estimates of these next states, so you will just back up from here to here. So it was like one step backup. On the other hand, Monte Carlo is like multi-step or like come up to the end of the episode backup, okay? But there is also another difference between these two. In the case of dynamic programming, right? So if you remember, when we talked about what kind of updates they are expected updates, because you consider all possible actions when you're updating, right? However, this kind of Monte Carlo methods are called as sample updates. Okay, why? Because from this current state, there are actually many possible actions, right? You did not consider all the actions while you're estimating your value function. So you only considered one sampled action. And from that one sampled action, again, there might be many possible states, but you're again considering only one possible state and so on. Okay, so in other words, like dynamic programming gives you expected updates, which is computationally expensive because if there are, imagine games with branching, very high branching factors. Okay, so chess or go, right? Like, so you have many possible next states. Like, so now expected updates are costly. On the other hand, you can do Monte Carlo, which is just sample based. So sample update. Is that clear? Okay, so I have a couple of more highlighting points about Monte Carlo. Like, so before we jump to how to estimate action values. Okay, so first note, I'm not sure if you have noticed this fundamental difference between Monte Carlo and DP, but in DP, you're kind of bootstrapping your estimates. Okay, so in DP, you're bootstrapping. So why do I say it's bootstrapping? Because estimate for my current state depends on the estimates of the next state, right? On the other hand, Monte Carlo is totally different approach, because in Monte Carlo, the estimates of each state are independent. There is no bootstrapping involved. Okay, so these are like two different approaches. Now, second note is, given that the action values, like the value estimates for the states are independent of each other, Monte Carlo is really like an attractive algorithm if you just want to estimate, if you want to estimate value of only one state. Okay, so DP, you cannot find a value of a state in DP without solving the entire DP problem, right? Because one state depends on other states, and other states depends on some other states, and so on. However, Monte Carlo is like a simple approach, because if you want to estimate the value of one state, you don't need to solve the entire problem. Like, all you have to do is repeatedly visit the state again and again and again, like whenever possible, and your estimate for the value of the state is going to improve. Okay, so there are many advantages in doing Monte Carlo when compared to dynamic programming. Like, so you're learning from experience. Like, so there is no requirement to have the transition probability, and you are not bootstrapping, like, which means you can just estimate action values for, like, state values for like just a subset of states. Okay, okay. So any questions so far? Okay, so now we can talk about, well, we are still not going to the control, like, so we are still in the prediction setting, but now let's talk about how to estimate action value functions instead of state value functions. Okay, so Monte Carlo estimation of action values. Okay. Okay, nobody asked me this question, so why would I do Monte Carlo estimate of state value functions? Can I construct the policy from Monte Carlo estimates of state value function? To construct the policy, like, what do I need? I have state values. Okay, now I want to construct policies from the state value. So
on the actions at each state.
what?
And just take the maximum.
Maximum of what?
We need action value.
You need action values. Okay, like, but we can still construct policies from state values without action values, like, but it requires a slightly different construction. I give you only state values, okay, and I ask you to construct the policy. How would you do that?
For each state, we see which action takes you to the next value, and then you just.
So
Yeah, but then you don't have access to that log distribution, right? So,
yeah, so like, I think that's a very valid point, right? Like, so if I just give you state value estimates and I ask you to construct the policy, the only way to do that is by, from this state, you consider all possible actions and then consider all possible next states. You pick the action which leads to the maximum state, valued state, right? But there's a problem here. The problem is this requires access to the transition probabilities, like, or at least it requires access to some model of the world which tells what are all the possible next states, right? So when you don't have that information, state values are not very useful. Like, so state values are useful when you can do one step look ahead in your world. Okay, when you cannot do one step look ahead, then you need action values. Okay, so moving forward, like I think we will focus more on the action values, because action values doesn't require the model of the world. If I give you Q functions, constructing policies is really easy, right? So what would be your policy? So the policy, like pi of A, is going to be just argmax over A, Q pi of A. Sorry, S comma A given S, right? So if I give you Q values, then it is very easy to construct the policy. Just check the Q values of all the actions in the state. Whatever action leads you to the maximum Q value, that is the action to take, right? Now, which means we should focus on learning the Q values, okay? But there is a problem in doing Monte Carlo estimate for Q values, okay? Now, if you think about it, we need an estimate for Q pi of S comma A, right? So what is Q pi of S comma A? It's basically expected return, okay? When starting in state S, okay, and taking action A, okay, and thereafter following policy pi, right? Now the problem in directly applying the Monte Carlo approach here is you have to, for every state, you have to visit every action infinite number of times to get a good estimate of Q values, right? We did not have this constraint with state value estimation, but in action value estimation, if you have a deterministic policy, it's not going to be useful, right? So imagine you have a deterministic policy, which for every state takes only one action. Now, you can never construct good policy from this, like from doing Monte Carlo with this deterministic policy, simply because you will not see other actions in the state. If you don't see other actions in the state, you don't know the Q values of these actions. And if you don't know the Q values, like how would you construct this argmax, right? So it's trivial, like you're not learning anything. So do you understand the problem? So how would we resolve this issue? Yeah.
Can you repeat why exactly is this an issue? Like you said that you for deterministic policy you cannot know Q pi. Why is that?
For deterministic policies, you don't get the Q value for all the actions in a state because you don't visit all the actions.
But you can start with every state and every action and then like follow the trajectory till the episode ends.
Yeah, but like our goal is to find better policies as well, right? So you will estimate, well, of course, you're going to estimate the action value for that particular action that you're taking. So that is not an issue. The question, like, but we are not just into, okay, here is the thing. Whenever we do policy evaluation, our goal is not policy evaluation, okay? So like, our goal is to keep this as one of the components in the whole control problem. Like, so eventually we do want to improve the policy, yeah?
Can we do the epsilon greedy approach?
Okay, well, that's a good solution. So
If you change our policy, we take different actions.
change the policy. Well, I think you both jumped one algorithm ahead. Yes, we can use epsilon. We can somehow combine epsilon greedy with Monte Carlo. Like we're going to do that. Yeah. Okay, so you're talking about switching. You're talking about another form of stochastic policy. Epsilon greedy is a stochastic policy, by the way, right? So It's stochastic because it takes all the actions with some probability. Now, softmax is another like stochastic policy where like you take all actions with some probability. Okay. Now, first let's start with a simpler solution than the, okay, this is actually like a very good solution. Like, but before we do that, we are going to talk about a simpler solution. Okay. So the simpler solution is the idea of exploring starts assumption. Okay. So the main problem that we are facing here is we need to explore other actions, right? So which is not a big concern in DP. You don't need to explore because like you have access to everything. But in this Monte Carlo situation, like you have to explore. Now, epsilon greedy is actually a really good solution. But before that, we're going to talk about like a simpler solution with very strong assumption. The assumption here is, what if I make this assumption that I can start every episode like with any state action pair that I want. Okay, so basically the episodes start in a state action pair, and that every state action pair has non-zero probability of being selected as start. Okay, now as you can see, this is like a very strong assumption. This assumes that I know I can control the start state. We are going to relax this assumption very soon, but for now, let's say that we can do this. Okay. Now you have a very simple algorithm which kind of guarantees that, like, all I have done is like I have slightly updated my previous Monte Carlo evaluation. Okay, so I'm just saying that I'm going to start with any state action pair that I want, which means I will consider every state action pair like enough number of times to begin. Then I can compute the entire return for that state action pair, right? So now I can actually use deterministic policies. It's okay, right? So
you're still using a policy, deterministic policy.
Yes.
So even if you start with any state action pair, it might have it might not go to the next state because the policy may say there is no action to take from the state.
There is a difference between policy being deterministic and the environment being deterministic. Okay, so the environment could be stochastic, so that could take you to other states. Okay, so when I say deterministic policy, it just means like from given a state, like I take only one action. Okay, so now in this case, we are still in deterministic policies. Okay, it is just that I had this very strong assumption that I can start wherever I want. Now, it's not always practical, right? Like imagine you are in a real like control situation, like a robot trying to control the temperature and other parameters of a power plant. Okay, now you cannot start with any possible configuration of the power plant. Like so, the state of the power plant is fixed. You have to start from there, right? Like, so you don't have control. For a lot of applications, you don't have control over the start state. So this is not a very practically useful algorithm, but it's going to be useful for us to build up our case. Yeah.
So you generally need the model to implement this?
That's a good point. So if you have a model to simulate, then probably you can do this. That's a good point. Okay. Now, the alternate solution, as everyone suggested, is to use stochastic policies. Okay, but we will first cover the deterministic policies case and then move to stochastic policies. Okay. So now I think we are ready to do the actual Monte Carlo control, which is basically finding the optimal policy. Okay. Now, we are going to follow the general idea of generalized policy iteration. Okay, so we are going to start with some random policy, okay, pi 0, and then we will use the evaluation, Monte Carlo prediction that we discussed before to come up with a Q function. Okay, from the Q function, I want to improve. Okay, now this improvement is happening by making your policy greedy, right? So then you do evaluation, you get q pi 1, and you proceed until finally you reach pi star and q pi star, sorry, q star. Right? Now, policy evaluation is done exactly like how we discussed in Monte Carlo prediction. Now, how do we do policy improvement? Here, right? So now the policy improvement is again same as the DP situation. Okay, so we are just going to revise the thing. So phi k plus 1 of S, the next policy is going to be argmax of A q pi k of S comma A. I have my current policy. For my current policy, I'm going to consider all the possible q values and take the maximum. So basically the greedy policy with respect to the q function of the current policy. Okay. Now, we already proved that this works through policy improvement. I'm going to redo it here. So just as a recap. So what I'm going to show you is the q, like the new policy is going to be better than the previous policy pi k, right? So let's consider q pi k of S pi k plus 1 of S. Okay. So what is the q function of okay, so I think yeah, okay. So what is the q function? I think I miss a, I think it should be k, or I'm not sure if this is k or k plus 1. Okay, we will do it and then we will fix it. Okay, so now this is basically q pi k of S comma argmax of A q pi k of S comma A. Right? My new policy is basically argmax over the previous q functions. Now this is equivalent to max over q pi k of S comma A, right? Now this is basically greater than or equal to q pi k of S comma pi k of S. Okay, this is nothing but b pi k of S. Okay, or in other words, the new policy, like the value function in the new policy, is going to be at least as good as the value function in the previous policy. It's simply because of the greedy policy that we are constructing, like, and it also holds from the policy improvement theorem. Okay, so now before I show you the full algorithm, I want to talk about the assumptions here, right? So we are making two strong assumptions here. Or in some sense, unlikely assumptions, okay? So the first assumption is that episodes have exploring starts. Okay. The second assumption that we are making is, if you think about policy evaluation, so policy evaluation is basically estimating from sample returns, right? For your estimates to get better, you have to see lots and lots of samples. Okay. So, or in other words, policy evaluation could be done with infinite number of episodes. Okay. Now, we should remove both these assumptions. It is kind of easy to remove the second assumption. So then we will remove the first assumption. Okay. Now, this is kind of like the same recipe. So can somebody tell me how to remove the second assumption? So we have seen this in DP as well, right? Like, so, like, the second assumption is basically your policy evaluation should converge so that you get good estimates. Then you do the improvement. So how can I improve this? So not this subgroup. So I really want answers from this column or that column or the Zoom folks. Yeah. Yeah.
Set a limit for the difference between two successive policies. Then
Sorry, can you please repeat?
set a limit, set some value, like epsilon, and then once the next policy is better by just epsilon, basically once the next policy is not much better than the previous one, then stop.
Oh, I'm not talking about stopping conditions for the whole algorithm. Like I'm talking about the point that just like how in DP, right? So there is a for loop inside the for loop. So you have a outer for loop because you're doing evaluation, then improvement, evaluation, improvement, right? Now, within evaluation, this evaluation, like to become more reliable, you want to see more estimates because this is sample average, right? Like, so by law of large numbers, like as time goes to infinity, this becomes the actual expected value. But you have to do a lot of episodes. So the question is how to improve on this algorithm so that I don't need to do a lot of episodes before doing the improvement.
After every episode, you change, come back and.
Okay, so after every episode, you just go to the improvement. So it's kind of similar to value iteration, right? So we kind of give up on the fact that, okay, we can continue until we find out. Okay, so we can kind of give up on the fact that we are going to find the best estimates in policy evaluation, okay? So what matters is as long as the policy evaluation is moving one step better, okay? So as long as you're making some progress in policy evaluation, it's okay to interleave these two things and you're going to converge, right? So now that is what our algorithm is going to look like, okay? Now here is Monte Carlo ES or exploring starts. Okay, so this is a control algorithm, which means this is not evaluation. We are going to find the optimal policy here. So you're initializing your policy arbitrarily. You're initializing your Q functions arbitrarily. Okay, and for each state, you have this return list. Okay, now this is the ES assumption. So you're going to choose all possible state action pairs, like probability not greater than 0. Okay, so this is the exploring states assumption. Now, starting from this state, you create an episode. Like, so you interact with the world and generate a trajectory. Okay. Now you go back in time to construct the return as usual. We have seen this before. Now we are doing first visit. Okay, so this is actually first visit Monte Carlo ES. So unless this pair appears before, if this is the first visit, then you're appending it to the return. Now you are also constructing the Q value, which is basically average of the return. Okay, so if you stop there, that is evaluation, but we are interested in control. So the policy is updated immediately. Okay, so the policy is basically argmax of. Okay, I don't wait for the evaluation to converge. Like, so I immediately update the policy. So which means when I do the next episode, I'm going to work with a new policy, and I will keep on improving the policy, and eventually this policy will converge. Okay. Now, intuitively, this Monte Carlo ES, right, should converge to the optimal policy. I can give you a lot of hand-wavy arguments. Okay. However, like more formal convergence proof for Monte Carlo ES is still an open question. So there are some proofs which talks about how this algorithm will converge in specific settings, but the general convergence proof for if you are theoretically inclined, like so the general convergence proof for Monte Carlo ES is still an open question. So it is not proved that this algorithm is going to converge to the optimal policy for all possible situations. Question?
Yeah, do you also have every visit variation for when you are doing Q values?
Yes, it's very simple, right? So how would you change this to every visit?
No. If my question is like, wouldn't that introduce some sort of bias if you do every visit?
Yes, that's true. Every visit is biased.
Like, for V functions, it was not because it was like you only care about the states, but when Q functions, you are also taking care of action and then.
Yeah. No, that is true. That is true. So, well, probably I will talk about the bias of these algorithms a little bit later, but we will talk about it today. But you're right. But how would you convert this to an every visit algorithm? Anybody? Yeah.
Remove that unless the pair appears.
Yeah, you just remove this line unless the pair appears, right? Then it becomes an every visit algorithm. So it's very easy to implement every visit if you have first visit. Okay. Okay. So now we talked about how to find optimal deterministic policy, but with a very strong assumption of exploring states, right? So finally, we can remove that assumption and see how to construct action value estimates without this restrictive assumption. Okay, so we're going to talk about Monte Carlo control, okay, without exploring stars. Okay. As I mentioned before, like if we want to avoid exploring start, the only way to make sure that is to keep selecting all the actions, right? Now this requires or this demands that the policy be stochastic, or sometimes also known as soft policies. When I say soft policies, they give some probability of for all the actions. Okay, so this just means that the probability of any action given yes is greater than 0 for all states and actions. Okay, now we have already seen one example for stochastic policy, which is epsilon greedy, right? So in the case of epsilon greedy, all the actions are taken with some probability, right? Like so, specifically for non-greedy actions. Can someone tell me what is the probability of taking a non-greedy action?
Epsilon.
It's epsilon, right? So like now it's epsilon. Oh wait, it's not epsilon. I'm talking about taking probability of taking one non-greedy action. Let's consider some action A, okay? A non-greedy action A. What's the probability?
Epsilon by total number of actions.
Epsilon by total number of actions, right? So it's basically epsilon by cardinality of the actions, right? Now, can someone tell me what is the probability of taking a greedy action?
1 minus epsilon.
What?
1 minus epsilon by
1 minus
Minus epsilon.
epsilon, is that right?
First.
Plus, even during random action, there is a chance, 1 by k chance of taking that action, right? So plus epsilon by cardinality of the action space, right? Now this epsilon greedy is one example of epsilon soft policies. Okay, now I'm going to define the general class of epsilon soft policies. Okay, now the general class of epsilon soft policies is basically any policy where the probability of taking an action is at least epsilon by A of S for some epsilon greater than 0. So then that is an epsilon soft policy. Okay. Now, as you can imagine, epsilon greedy is probably the most greediest epsilon soft policy, right? I can construct other epsilon soft policy. For example, the softmax policy, like that he mentioned, right? Like so, you can have different probabilities for all the 5 actions. Let's say you have 5 actions, you could have each probability of 0.2 uniform, right? Like 0.2, 0.2, 0.2, 0.2. So now that is still an epsilon soft policy, right? Like you can have any type of epsilon soft policy, and epsilon greedy is really the closest to greedy. Now, our goal is to go as close as possible to greedy, right? Like so, when we converge, we want to converge to this policy which works well as much as possible, like which means the epsilon should not be very high. We want as greedy algorithm as possible. So epsilon greedy is probably the most commonly used epsilon soft policy, like if we are learning a soft policy. Okay. Now, let's look at the first visit Monte Carlo without epsilon, like without exploring starts. Okay, so here is the algorithm. So you have first visit Monte Carlo for epsilon soft policies here. So it's very similar to the previous Monte Carlo algorithm. Like, so the one, like, initialization is same. The only difference is you see that you are no more required to start from every possible start action. Okay, you can generate any trajectory that you want, okay, by using the policy. Now, when you update your policy, right? So the policy update is epsilon greedy. So after you do the evaluation, like one step of evaluation, you find the argmax. Now for argmax, you set the probability to be this, and for other actions, you set the probability to be this. Now next time when you do another episode, you will be using this policy for this state. Okay. Now, if you run this algorithm for infinite number of times, then you would have visited every possible state action pair infinite number of times, which means this algorithm will converge to the actual value estimates and hence the optimal policy. Okay, so I guess there are convergence guarantees for this algorithm. So it's easier than the exploring starts algorithm. Any questions about first visit MC with epsilon soft policies? Yeah.
You said actual value estimates, that I agree, but I don't agree it will converge to optimal policy, right? It's doing this kind of exploration all the times.
Oh, that is true. Okay, so the policy might not be optimal, but the Q functions should converge, right? Yeah, sorry. Okay, I'll rephrase my statement. Like, so the Q functions will converge. Okay. Now, if you want a deterministic policy, you can just stop epsilon greedy. Like, so you can set epsilon to 0 then.
You're basically exploring the policy.
Yes. Okay, any questions? Yeah.
It's like more generally when you have a stochastic policy, so like evaluation and improvement are going to be like this. And once you converge with your Q values, then you simply stop being stochastic and start being deterministic. Is that how you do it? Or
Okay, so that is a good question. So the question is, should you convert your algorithm to a deterministic algorithm once you converge? You can do that, but well, probably I will not talk about the fact that I'm not sure if I'm going to talk about it or not. But the point is, when you converge here, you'll converge to the best possible epsilon soft policy. Okay, so what we have done here is we removed the assumption of exploring start, but that comes with the cost. The cost is we will converge to the optimal policy among the class of epsilon soft policy. Okay, so we will not converge to the optimal deterministic policy. Now, I think you can construct the deterministic policy from this, but I don't want to talk about the convergence guarantees because I'm not sure. Okay, but in practice, like whenever, well, probably this discussion will be more relevant in the third half of the lecture. So after the break, we are going to talk about off-policy methods, like where you're going to separate the policy that you're using to explore and the policy that you're learning. Okay, so then the policy can be deterministic, like so whatever you're learning, but still have a stochastic policy for exploration. That's jumping 20 minutes ahead. So probably we will stop here and continue our discussion on Monte Carlo methods after 10 minutes.